Computing truth values. In the previous unit, we looked at the logical connectives and sort of presented you with the 5 basic connectives that we'll be using throughout the course. We also discussed how to identify the main connective of a compound or complex statement. So at that point, we gave you sort of a basic understanding of what the connectives are. All right, so we gave you a conjunction, an and statement, an or statement, an if-then statement. But we didn't give very specific meanings to those. And so what we're going to do in this chapter is define each of those connectives and give each of those logical connectives a specific logical meaning. In addition to that, we're going to show you how to determine the truth value of a given statement when you know the truth values of the component statements. So going back to that very simple example of if I have a dog and if I have a cat, or I should say, I have a dog and I have a cat. When I give you an example like that, the truth of that statement depends on the truth of the two simple statements. I have a dog and I have a cat. So for that entire statement to be true, we have to know the truth value of each of the simple statements. So if it's true I have a dog and it's true I have a cat, then that whole statement, the big statement that I said, I have a dog and a cat, is true. On the other hand, we know in certain circumstances that whole statement might be false. Well, what would make it false? Well, what would make it false is if either it was false that I have a dog or it was false that I have a cat. Now that sort of idea, we can sort of present that informally, but what we're going to do in this chapter is actually give a formal presentation of all the possible truth values for a given connective. So we'll show you this in the truth table shortly. But then once you understand the truth tables and understand what makes a statement true or false, or under what conditions a statement is made true or false, then once we've done that, we can sort of give you statements and you can compute the truth value of those statements if you know what the truth value of the various pieces are. So this will become clearer as we go through the section. So what we're going to talk about here is the component sentences can only have one of two sentences. So when I talk about the components, those are the simple statements that make up the compound statement. And they can either be true or false. So in this system, since we only have two possible values, true or false, this is a 2-value logic system. Now I should note that there are other types of logic systems. There are 3-value logic systems, for example, where there's true, false, and maybe. So we're looking at this particular system, but just note that there are other systems that have additional possibilities, not just true or false. Now the truth value of any statement, as I've already alluded to, is based on the combination of the simple sentences and the truth values of those simple sentences. Now what's going to be very important here is in order to determine the truth value of a long, compound, or complex sentence, we have to identify the main connective, because the truth value for any given statement is always going to be the truth value under that main connective. So that's why it's important from the previous chapter that you understand how to identify the main connective. That will determine the truth value for the entire statement. And then once we've identified the main connective, identified what the truth value of each of the components are, by using the truth tables that we're about to present, you'll be able to determine the truth or falsity of any given statement. Now the first connective we're going to talk about is the conjunction. So you see here in the conjunction is the and statement, which we've presented before. And in the conjunction, when the left conjunct is true and the right conjunct is true, then we say the entire statement is true. I have a dog, I have a cat, it's true I have a dog, it's true I have a cat, therefore I have a dog and a cat is a true statement. Notice here then that if the first statement is true, I have a dog, but it's false that I have a cat, then the entire statement, I have a dog and I have a cat, is false. It's also the case if it's false that I have a dog, but true that I have a cat, my whole statement is false. And of course, if both of those are false, I've just outright lied to you. So if it's false that I have a dog, it's false that I have a cat, then the entire statement is false. Now, you will, or it would be good for you to memorize these truth tables. So one easy way to remember this truth table is just to say, in a conjunction, the only way a conjunction is true is when both conjuncts are true. So if I remember that and I remember any other combination is going to be false. So a conjunction is true. And again, notice that we're looking at the conjunctions under the main connective, the dot. So the left side is just the truth value of P, the truth value of Q, and we're actually sort of substituting in on the right side, P and Q. So when P is true and Q is true, P and Q is true. But this is what you should remember is this first line here. A conjunction is true when both conjuncts are true. Everything else is false. So that's pretty simple. And quite honestly, you can actually figure this out for yourself. Just in the way we use the word and, you can sort of recreate this truth table. But it's often helpful just to sort of see this all systematically put out in front of you. The next connective, material implication. So material implication is the horseshoe statement. And so we want to know what the value is under the horseshoe statement. Again, it depends on what the values are under the antecedent and the consequence. So in this case, in the first line, if P is true and Q is true, then P therefore Q is true. Now, if P is true and Q is false, then the horseshoe statement is false. If P is false and Q is true, it's true. And if P is false and Q is false, it's true. Now, the first one seems pretty clear. This first row here seems pretty self-evident. If I say that if you study, then you pass, it's true that you study, it's true that you're passed, then it seems that if you study, then you will pass is a true statement. It also seems pretty clear that if you study and you don't pass, then the statement, if you study, then you'll pass, is clearly false, right? So this one also seems intuitive. The last two seem to be less intuitive. So it says, if I said to you a statement like, if you study, then you will pass, and I said it's false that you study, but it's true that you passed, well, then why is this still true? And similar, if it's false that you studied and it's false that you passed, why is this true? Well, I'm going to give you two sorts of explanations or ways of thinking about it. The first one is going to be very pragmatic. Just accept the truth table for what it is. In other words, when doing the work, the most important line in this truth table, or the most important row, I should say, is this center one. You know that a material implication is only false when the antecedent is true and the consequent is false. So for memorization purposes, for keeping it clear, that's the row that you're most concerned with. Now, when we're talking about these last two rows, so rows 3 and 4 here, if it's false that you study and it's true that you pass, in some ways we can think of this as, well, my initial statement was, if you studied, then you passed. I said nothing about the situation if you didn't study. So if it's false that you studied and it's true that you passed, we still want to say, well, if you study, then you'll pass. So we might look at it as, well, I said nothing about that other condition, so it still holds true. And in some case, it does actually make some sense as well, right? So if you study, then you'll pass. If it's false that you study and then you still pass, well, it seems clear that had you studied, you would probably still pass, assuming, studying here, of course, they're assuming that you studied properly and so forth. So in some sense, that line 3, or that row 3, it kind of makes sense. When they're both false, it follows a similar sort of reasoning, right? So if it's false that you study and it's false that you passed, neither of those say, or it's almost a counter to the first, well, see, it's false that you studied, it's false that you passed, and it seems that if you studied, then you would have passed. So there's seems to make a sort of intuitive sense that this last row also sort of makes sense. Now, again, if you don't like the sort of truth table, the material implication, there are others who have argued that there's some rows in the material implication that should remain undefined. In other words, rows 1 and 2 here, those are fine, maybe even row 4, but maybe we should get rid of row 3 and just leave it as blank as it's something we can't define. I think there's good reason, intuitive and logical reason to say, yes, this truth table holds and we can accept this. So for our purposes here, we're not going to debate the merits of the material implications definition the way it's been defined here. We're just simply going to say, if the antecedent is true and the consequent is false, it's false. Any other combinations of trues and falses for P and Q, thinking here, any other combination you substitute in, that whole statement, if P then Q, is going to be true. Now the disjunction, the or, is sort of in some ways almost the opposite of the and in terms of its truth value. Now, I should note there's two different types of or statements. There's an inclusive or and an exclusive or. In our day-to-day life, we often talk in terms of exclusive or. So if I say, I'm either going home or I'm going to my office after class, Normally what you would say is it's got to be one or the other, but not both. And in logic, that's what we would call an exclusive or, right? It doesn't allow that if both statements are true, that the or statement is true. In our case, we have what's called an inclusive or. So this disjunction of the or is inclusive because it allows that if I both go to my office and go home, that is acceptable. That still is a true statement. So if I look here, I said P or Q. If P is true and Q is true, then of course the whole thing is true. If P is true and Q is false, then it's true. And again, if I say I'm going to my office or I'm going home, I end up going to my office, but it's false that I go home, then that statement still seems to be true, just in the way we use sort of English in everyday discourse. If it's false that I go to my office, but true that I go home, my statement that I'm going to go home to my office or I'm going to go home is also true. And if it's false that I go to my office and false that I go home, say I end up going to the library or going to get something to eat, then it's clear in that case that I have lied in some way. In other words, my statement, my overall statement, I'm going to go home or go to my office is false. Now, as I said, but there's another interpretation of the disjunction in the exclusive sense in which I can't do both things. Now, in logic, when we want to imply that it is exclusive, that we can't have both, we would sort of rewrite it in the following. I'm going to do P or I'm going to do Q, but I'm not going to do both P and Q. So when you need, for purposes of translation, for example, or you want to be very, very specific about how you're using or, if you want the exclusive sense, then this is how you would actually translate an English statement into exclusive or. Now, as I said, in a lot of times, we sort of assume an exclusive or because a lot of the times we use or, we can't do both things. So, for instance, on Friday at 1 o'clock, I can't go to a movie or go to the park at exactly the same time because I can't be in both places at once. So it has to be one or the other. So when I say I'm going to do one or the other, for that whole statement to be true, I'm going to go to the movie or I'm going to go to the park at 1 o'clock, it would have to be exclusive. I'm going to go to the movie or I'm going to go to the park. Now, here's a case where you might say it doesn't matter. What if the movie's being shown in a park? In that case, it can be true that I'm both going to the movie and going to the park. So if there's an outdoor movie, I've actually fulfilled both requirements and my statement is still true. I'm going to do one or the other. Well, it turns out I can do both and it still be true. But for what we're going to be doing in this course, many times an inclusive or is perfectly fine with the way in which you translate the sentences. And our true table, though, in terms of memorization, this is the row that you want to focus on, this last one, where P is false, Q is false, then P or Q is false. Any other combination of T's and F's in an or statement are going to end up being true. So it makes it easier to memorize. Okay, what's a disjunction? Disjunction is false only when both disjuncts are false. Any other combination. So you don't have to actually go through and say, when P is true and Q is true, it's true. When P is true and Q is false, it's true. When it's false and true. You don't have to try to memorize each of those, just knowing the one sort of essential row. The rest of them, it doesn't matter what the combination is, it's going to end up being true. So that's the disjunction. The biconditional, if and only if. And the biconditional is interesting in that the way in which I think of a biconditional is when both of the biconditional, the left and right side, are the same, then the statement is true. When they're different, it's false. So in some ways you can think of, and again, this is not technically accurate, but you can think of the biconditional as kind of like an equal sign. When both of those two things are the same, then that statement is true. If they're different, then it's false. So you'll notice here, when P is true and Q is true, the biconditional is true. When P is false and Q is false, it's true. So in both cases, when the two statements are the same, it's under those situations that the biconditional is true. Any other combination is false, right? So when P is false or true, Q is false, then it's false. When P is false and Q is true, that is when they're different. So in these two cases, when they're not the same, then we know it's false. So again, part of this, when we're doing actual problems, you should have the truth tables written out right next to you. You have the book. You can photocopy in the cover of the book, photocopy the truth tables. But it's good to have these written out next to you so that you can easily refer to them until you've got them memorized. After doing enough problems, you really will commit most of these to memory pretty quickly. It's really not that difficult. But again, here to remember in the biconditional, how do I know when a biconditional statement is true? Both sides of the biconditional have the same truth value. The last one is the negation we have to cover. And negation is fairly simple. And negation just flips the value of whatever the statement is. So if P is true, then not P obviously is false. So the negation in front flips the value. If P is false, then not P is true. And so that's pretty easy. There's only 2 rows in the negation with the negation, and it simply changes the value, swaps the value from whatever it is. Now, when we're going about determining the truth value of a particular statement, we'll start by actually giving you the values of each of the components of the statement. So we'll show this in a minute, but here are the sort of steps you should go through when beginning to do or computing the truth value of a given statement. So first thing you want to do is look at the expression and find the main connective. And this is true whether you're translating from an English sentence into symbolic notation or if you are already given the expression in symbolic form. You still want to determine what's the truth value the main connective, because once I know what the main connective is, then I know what determines the value of the entire expression, regardless of what all the other compound statements are. Since they're all held together by that one connective, the ultimate value of that whole statement will be determined by the main connective. The next thing you're going to do is assign truth values to each of the variables or the letters that are given to you. So you want to sort of write those down immediately, and then begin with what's in parentheses and work your way out, just like you would in sort of mathematics, determining the truth values using your truth tables. So I'll give you a number of examples so you see how this whole thing sort of works out. So let's say I'm given the following. A, B, and C are all true. X, Y, and Z are false. So here's my big expression right here that I want to say, what is the truth value of this whole expression when A, B, and C are true, X, Y, and Z are false? So the first thing I do is I determine the main connective. So again, when I look here, it seems that I've got parenthesis here, 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 and here. Well, this seems to be one whole statement. And I've got matching up here with my parentheses. I see, oh, this whole thing is the antecedent on the left side, right? So what begins with not X, therefore not A. So I know that this is going to be my main connective. So the value of this entire statement is going to be determined by whatever the value is that falls under that horseshoe statement. Now, what does that mean? It means I have to know the truth value for that whole thing. And if I know the truth value for that whole thing, then I can determine it from my truth tables under the horseshoe, right? So if this first half over here ends up being true, say, and this false, then I know that the whole thing is going to be false. Now, how do I know that? It's because I look at my truth table. Now, I don't know yet, right? That's just an example. I don't know yet what the value is of these two parts. So the first thing I'm going to do is assign the truth values. Well, it's already given to me that X is false, A is true, Z is false, Y is false, A is true, X is false, and C is true. So that's step one. Now, it doesn't matter where I start. I can start on the left side or the right side. So let me start on the left here. If X is false, then not X is clearly going to be true, right? Now, how do I know that? I go to my truth table for the negation, and I know that if P is false, then not P is true. Well, the same goes for A. If A is true, then not A is false. Now, when I look at this, I say, well, I have this horseshoe statement now connects true, horseshoe statement, false, right? If T, then F. I have T, therefore F. And if I say, well, what's T, therefore F? We'll go to my truth table for the horseshoe statement. And I look and I say, oh, wait, when the left side is true, the antecedent, and the right side is false, then this whole thing is false. Now I do the same with not z and not y, right? I know that y is false, so not y is true. Z is false, so not z is true. So I have true and true, right? So there's my little and right there. True and true. Well, if I go to my truth table for the and statement, I know that the and statement is only true when both conjuncts are true. So since they're both true, I know I've got true. And now the sort of sub main connective for this whole big piece on the left here is the and statement. So false and true. I have false and true. I know, again, because I know my conjunction, I can look at my truth table. I see when the left side is false and the right side is true in a conjunction, the whole thing is false. So now I've got the left side. Now I go over the right side and I look and I start again, starting with what's in parentheses, A, therefore X. A is true, X is true or false. True, therefore false. Well, again, if you don't remember, we just learned these truth tables. If you don't remember, just go to your truth table and say, oh, what happens in a horseshoe statement where the left side is true and the right side is false? True, therefore false is false. Now I still have this or to contend with, right? So I've got false or what? True. So I'm just going to bring down that true. Make it easy just to keep it straight. False or true, when I look at my truth table for the disjunction, and I remember that, wait, when is a disjunction false? It's when they're both false. Any other combination is true. So in this case, I have false or true, therefore it must be true. And then finally, I can take this, the false on the left side, the antecedent, and I've got true on the right side, false, therefore true. And again, I look at my truth table, I say, well, the conjunction or the material implication is only false when the left side is true and the right side is false. Anything else is true. Therefore, I know the entire thing is true. Now again, the only difficult part about this really is keeping everything straight. Now, if you're wondering, I'm going to two things. If you're wondering why A, B, and C are true and X, Y, Z are false, that's just the letters or the values we've chosen to assign. So in any example, I could say A is true, B is false, Y is true, Z is false. I could give you any combination, and that's just sort of the key, right? So what we're attempting to do here is have you use the truth tables to determine the values, but those values are just happen to be arbitrary. Like those are just chosen by examples in the book or myself. So that's one. Two, you might have noticed, you might notice that when we were determining the antecedent, so when we looked at just this half, that if I know this first half is false, then I really don't have to know anything that's going on the right side. Now you say, well, why wouldn't you have to know? So when I get to, for example, this point or this point, now notice here that when this side became false, I knew that that conjunction automatically was going to be false. So I could already tell, regardless of what was going on over here, that we were going to end up with a false. But let's say I got to this stage. It turns out that if I really know my truth tables, then I know that if the antecedent is false, it doesn't even matter what the value is of the consequent. All right, so if you remember, P, therefore Q. So if I look at all the possibilities, so I'll do a little mini truth table here. True, false, true, true. All right, so when I look at this, I know that this is the only case in which that becomes false. The minute I see a false over here, it actually doesn't matter what the value is on the right side. Right? So if I have false in the antecedent, it doesn't matter whether the consequent is true. It doesn't matter whether it's false. It's still going to come up true. So as you go along doing truth tables, you'll start to notice some of these where you actually could, in principle, just simply skip the entire second half. Right? So this antecedent over here and this consequent over here, you actually wouldn't have to worry about doing those. In the consequent, you wouldn't have to worry about working those out. Now, if you didn't see that, you weren't thinking that way, that's fine. At this stage, you should just be getting used to doing the truth tables, working through the process, going all the way to the very end. But as I said, later on, you may actually be able to identify the fact that, oh, yes, I can see already that I know the value of this without having to go through all the extra steps. So let's take another example. If A, B, and C are still true, X, Y, and Z are false. And let's take this statement here. So I have this whole statement here. Again, I can sort of see that these two parentheses line up. So this is one whole piece on this side. I can see that I have not the quantity X and Y in parentheses here. So this whole thing is also one piece. So the main connective in this case is going to be the biconditional statement. So ultimately, to determine whether this statement, this whole statement, is true or false, I have to find it under the biconditional. Now again, when I'm doing this, I can start on either side. Let me make some room here for myself. So I can start on either side, and the first thing I'm simply going to do is assign the truth values that are given to me. So X is false, Y is false, A is true, and false, false. And then the next thing I'm going to do is the negations. So X and Y are both negated, so that makes not X true and not Y true. And since I've got so much done already here on the left-hand side, I'm just going to go ahead and do this. So I've got true and true. All right, true and true is true on this side of the biconditional. Now on the other side, I do need to know what's right. So the biconditional that alone doesn't tell me anything about what the value of the biconditional is. I've got what's in parentheses first. So I might say false and false. Well, I know false and false is going to be false. And again, if you don't know why, go look at the conjunction truth table. Note that when the left conjunct and the right conjunct are both false, the whole thing is false. Now this negation means I negate what's ever in the parentheses. So if X and Y are false, then not the quantity X and Y is true. So now I have A is true, therefore true. So I have true, therefore true. And I know from my truth table, when is a material implication? When is a horseshoe statement false? It's only when the antecedent's true and the consequence false. I don't have that, so therefore it's true. And now there's that biconditional. Now again, if you remember the biconditional, I said think of it as an equal sign. As long as both sides are the same, the expression is true. So I get true if and only if true is true. And that gives me the truth value for this entire statement. So again, you see here the important part is once you've identified the main connective and you slowly work from the inside out, starting with what's in parentheses and working out, it's pretty easy to determine the truth value of the given statement. So this example. So we have now one that's just all biconditionals. Again, the values are the same. So start with the main connective. Well, this is kind of nice and easy. I've got two sets of parentheses that match up. Tells me that this is all one piece and the second part is all one piece. So again, assign my truth values. I've got A is true, B is true, Z is false, X is false. Now I know I've got a biconditional here, so when they're both the same, I know they're true. Over here on the right side, Z is false, X is false. When they're both the same, I know they're equal or true. And now I've got true if and only if true, which also tells me that the entire expression is true. So again, this is why the identification of the main connective from the previous chapter is so important, because once you know that, then you can sort of break these problems down into their smaller pieces. And then it's just referring to the truth table. So everything I'm doing here is simply fill in the blank. A, if and only if B, A is true, B is true. I just go look at my truth table, find the value. Z is false, X is false. I look at the row in the truth table that says false on one side, false on the other for the biconditional. Oh, that's true. I write it down. Now it's true, if and only if true, that gets me true. So again, this is pretty much plug in and simply refer to the truth tables to solve. So the hardest part is the main connective and making sure that you're doing things in the proper order, right? Starting with what's in parentheses and working your way out. So another example, A therefore B or X. So again, I'm simply going to assign my truth values. I know A and B are true. X is false. Start with what's in parentheses. I've already identified that OR is the main connective. Right? This whole thing is one piece, and that letter is just one piece. A, therefore B, I look at my truth table, and I see that when A is true and B is true, the entire expression is true. This, on the right, the X, I have nothing to do. So I simply just bring that down, right? That's just X is false, there is nothing else. True or false. Well, I look at my OR statement. When is an OR statement false? Only when both disjuncts are false. Otherwise, it's true. And so the value of the statement is true. And again, this is just knowing two separate truth tables, right? So there's the horseshoe truth table. This is why I say it's really important that you write these out, keep them next to you so that you can remember, sort of quickly refer to them and start to remember them without actually having to consult the truth tables. So that's one, as long as I have that table next to me, and I need my OR statement, right? So just to go over this to make sure we're completely clear on this. Here's the OR truth table, true, false, true, false. And we got true, 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 and false. Right, so here's the OR table. So in this first part, when I'm looking at true and true, I go to my truth table over here and say, oh, true and true, therefore true, say, is true. And that's where it is. I got it right there. The false is simply false. There's nothing more to refer to. And I've got true or false here. Well, when it's true under the ORs table, when it's true here, false here, it's false is the value. I'm sorry, true as the value. And that's exactly what I got. Right? So when I look at that row, say the left side is true, the right side is false, the whole thing is true. So I give one final example here. This is a good time to take a moment to pause the video, try it on your own before I actually work through it. So not the quantity A or X, therefore not the quantity B, therefore Z. So again, step one, identify the main connective. Okay, well this, again, seems pretty straightforward. This is the antecedent. This is the consequent. That's the main connective. Now, what do? I assign the truth values. So A is true, X is false, B is true, Z is false. Now again, remember, always work from what's inside the parentheses out. So you don't want to apply the negation until you've done what's in the parentheses. So I go to my OR table, which we just talked about. When the left disjunct is true and the right disjunct is false, T or F is true. Now this I know is negated, so I have to take into account the negation, which means this entire thing is false on this side. Now over here, I have true, therefore false. And again, looking at the truth table for the material implication, the horseshoe statement, when the left side is true and the right side is false, that is false. But again, I have to now negate what's inside the parentheses. That makes it true. So the left side is false, the right side is true. False, therefore true. I know again from my truth table is true. Now here again, if you had simply done this first half and ignored everything on the second half, you don't actually need to know the value, right? So if you started on the left and said, oh, T or F is true, negate that it's false, oh, you're actually done with the problem because you already know that this entire expression is going to be true. Because again, P therefore Q, sorry about that. When you do the truth table, you get true, false, true, true. All right, so here again, the left side of this horseshoe statement is false. We already know right that. So what happens when the left side is false? Well, there's only two possibilities. True and true. Doesn't matter what happens over here on the right side, regardless of what it is. So again, you could actually stop the problem right at this point and simply say, yes, I know the whole thing is true. And by the way, if for homework assignments or exams, if you were to do the left side, write down true under that main connective and not do the work on the right, that would be perfectly acceptable, because you are demonstrating that you actually do know the truth tables well enough to identify that, yes, I don't actually have to know the value of that right side in order to get the value of the entire expression. When you do the truth table, now it should be also sort of emphasized that not all operators are truth functional. I'm not going to go into great detail. There is information in your book about identifying truth functional and non-truth functional operators. We'll talk a little bit more about this as we give you sort of a list for the purposes of translating English sentences into symbolic notation. So for an operator to be truth functional, though, the truth value of the compound that it forms is completely determined by the truth value of each of the components. So to be truth functional, it has to be the case that knowing the truth value of each of the components. So remember, a truth functional operator means we're dealing with a compound statement. So knowing those values has to completely determine the value of the statement. That's not always the case. So some words aren't acting as truth functional operators. So a truth functional operator will guarantee that the true-false outcomes, regardless of what's being substituted in. Now, one sort of classic non-truth functional operator, one that can be, is something like because or believes. So they don't necessarily, the word Joe believes something to be the case doesn't act as a truth functional operator. There's nothing, it doesn't guarantee that what actually follows, knowing the truth of the belief, doesn't in any way entail that what is believed is actually true. So Joe believes that the sky is full of ether, the sort of mysterious substance stuff that people used to believe in. The fact that Joe believes it doesn't make the statement, Joe believes that the sky is full of ether, doesn't make it the case that the sky is full of ether is a true statement. Right? We can say things about Joe and his beliefs, but the relationship between the two simple statements isn't necessarily determined by the truth value of each of those statements. One could be false, one could be true. Joe could still believe. So what is it we're actually trying to say? So your book gives a very nice explanation of some of these non-truth functional operators. For our purposes here, the truth functional operators will be pretty clear for you. So in terms of our translations, and when we get to symbolic form, the need to determine whether something's truth functional sort of fades away, right? Because everything that's already been translated into symbolic notation, we can already assume is in fact already a truth functional operator. So it's just interesting to note, and it's worth keeping in mind, that not everything that sounds like a truth functional operator is actually a truth functional operator. So I'd encourage you to read, it's in Unit 3, Section 4 of the textbook. It'd be a good idea to read that just to be up on that. But what's going to be most important from this chapter is the following: being able to compute the truth value of a statement by substituting in values that are given to you and then applying the truth tables to that statement, right? Identifying the main connective, identifying all the sort of sub statements, the simple statements, and determining their truth value in order to determine the truth value of the entire statement. So that's all we have to say about truth functional operators. We will note that in later chapters, we'll be returning to the truth tables to use them in cases where you're not given specific values. In other words, you're not told A, B, and C are true and X, Y, Z are false, but we want to know whether the statement is true or false, under what conditions the statement is true or false for all possible substitutions, right? So in this one, we're giving you specific substitutions. We're saying X, Y, and Z are false, A, B, and C are true. Now, what's the truth value of a statement? Later on, what we're going to be doing is saying that particular statement, whatever it is, I want to know what all possible truth values are, given all possible combinations of truths and falses. So if I change every one of those letters, one can be true, and this can be false, and that can be true, and this can be false. Every possible combination. And we'll be doing more with truth tables later on for determining whether arguments are valid or invalid. So right now, all you should be focusing on is just being able to determine the truth value of individual statements by substituting in values given to you and then applying your truth tables.